In this video, we're going to look at a practice problem for LeChatelier's principle. Remember, LeChatelier's principle tells us that when we have a system that is initially at equilibrium, that if we change the conditions of the system, that the equilibrium will react in such a way that it is though it is undoing the stress that we provided. In other words, if we increase a reactant concentration, the reaction will go in the forward direction to use up that reactant. If we reduce the concentration of a reactant, the reaction will go in reverse to replace that reactant. So let's look at an example using this reaction. We did this demo in class, and there is a video of this demo elsewhere on the YouTube channel. So this is involving cobalt ions, and when it's in the chloride form, it's blue. When it's in the aqua or water binding form, it's pink. So what color does the solution change upon each of the following changes? That should be a question mark. The solution is initially purple because both ions are present. So we prep the solution in such a way that both this ion and this ion are both present. We get a purple solution to begin with. And so we're going to go through each of these changes. So what happens if we add some HCl? Well, HCl doesn't appear in our reaction, but chloride minus does. We know that HCl is a strong acid. It'll dissociate completely into forming H plus and Cl minus ions. Those Cl minus ions will increase the product concentration of chloride and make the reaction go in reverse. When it goes in reverse, this reaction will turn blue. The system is heated. Now we're given this additional piece of information over here that the reaction is endothermic. Remember, a delta H that's greater than 0 implies endothermic reactions. Endothermic reactions absorb heat into them, so we're going to treat heat as though it is one of the reactants. All right, so we're going to put heat over here on our reactant side. So if you heated the system and the heat is a reactant, that's going to drive the reaction in the forward direction because the heat is now being treated just as though it's any other reactant. So that's going to drive it in the forward direction. That's going to turn this guy pink. What happens if we add silver nitrate? Now this one's tricky because silver nitrate's nowhere in here. However, we're reminded that silver chloride is insoluble. And what that hint is trying to get at is that chloride, remember, does in fact appear in our equilibrium. And so if we were to add silver nitrate, this reaction would happen. We would be forming solid silver chloride in the beaker that this reaction is happening in. And what that would do is it's using up chloride ions. So that's reducing the concentration of one of our products. The system will shift to make more of the products that we're removing. So the equilibrium is going to shift in the forward direction to replace those chlorides. That's going to turn this reaction pink. All right. What if we added potassium nitrate? We're given a hint here that this is unreactive with all species, which isn't surprising because we know that K plus and nitrate are always going to be spectators under every condition we've seen in general chemistry. So because this doesn't react with anything, it doesn't change the temperature, it has no effect on the position of equilibrium, all right? So when we add things that don't react with any of the reactants or products, it's not going to have an effect on the Q value. In other words, it's not going to affect the position of equilibrium. So in other words, here there's no change, which means this reaction, or under these circumstances, the reaction is going to remain its initial purple color. All right, so that's LeChatelier's principle as a practice problem. Remember that we're going to look at our reaction carefully and ask ourselves, is a change adding to a reactant or removing a reactant, or adding to a product or removing a product? Is heat a reactant or a product based on whether the reaction is endothermic or exothermic? And then we're going to use those to predict whether or not a change is going to push the reaction in the forward or reverse direction.